Welcome to a lesson with Dr. Powell. Let's continue where we left off last time in the last video, where we found a recurrence relation that was different than the one we started with. So in the last video, we started with one that looked like a sub n plus 1 is equal to a sub n plus 3 to the n. So we started with this and we converted it into this. And the way we did that was via series and a polynomial and factoring and so forth, and we got able to get this. So it's kind of a neat idea how you can take a recurrence relation like this and convert it completely to one like this. This is called like a homogeneous type recurrence, and this is called a non-homogeneous. Notice how you have extra things added on right here, and here you simply just have a multiple of this guy and plus a multiple of that other guy right there of two previous terms in the sequence. Okay, so this is where we're at, and let's go through the process of actually finding the finishing this off and actually finding that what the recurrence, what the nice equation for a sub n would be. Now, if you recall from last time, it was mentioned that this is our goal. That's what we're aiming for. Okay, so that's what we'd like to see. So let's go through that. We're going to write this as a matrix type equation. The way we do that, yes, and the way we do that is if we put the -3 right here and the 4 right here with a 0 and a 1, you can double check that if I were to plug in something like a 0, a 1, notice what happens. This would end up being a1, and then down below this becomes -3a0 plus 4a1, and it's going to be equal to a2, and that's what I want. And my formula is going to end up being 1. If I put a 1, 0 here, that picks up the top entry right here. So just be an. All right, that's just equal to a or a1, I guess. And if I change this to the nth, so to the first power, it gives me a 1 there. If I raise it to the nth power, this gets me a n. So this is the formula that I like. Okay. And so somehow I need to show that this formula is the same as that one. And we'll do it via a simplification of the matrix power of this to the nth power. So let's go for it. How do we figure that out? Well, as stated in another video, all we need to do is think of this matrix as being the same as a scalar x, and we multiply by scalar x. It's like multiplying by this matrix. And to say that they're the same thing, so we can think about polynomials of this matrix, is the same thing as saying that this matrix minus that one is the 0 matrix. Okay. Now that's the same thing as saying x and x minus 4, 3, and -1 is a 0 matrix. And in particular, the determinant will be the 0 matrix. The determinant's a polynomial, and it'll be a 0. So if we just work in mod arithmetic of that polynomial, we'd be good in order to simplify calculations with our matrix. So, because the determinant of a 0 matrix is just 0. So just take the determinant of this matrix. Okay, so taking the determinant of that matrix, we get x minus 4, then minus a -3, so plus 3, That's x squared minus 4x plus 3. Now we can, if we factor this, we end up getting -1 minus 3, and that works. Okay, so now in order to work through this, what we're going to do, let's use polynomial modular arithmetic in this case in order to do this. That means we want to find a simpler representative of x to the n mod that. Okay, so we know, since this is quadratic, that the simpler representative will be something like ax plus b plus some multiple, so something, some kind of polynomial, whatever it is, times x minus 1, x minus 3. That's what we're looking for. Okay, and actually, since it's mod, I guess we've written equality. X to the n is equal to ax plus b plus some multiple of that. They're equivalent mod this, but equal this if we just say that's some kind of multiple. Now this is great because if we plug in 1 into this equation, this part goes away no matter what that multiple is, because x1 minus 1 is 0. So that's out of the picture. And then we're just left with 1 to the n is equal to a plus b. Great. Okay, now what if we plugged in 3? We'd get 3 to the n is equal to 3a plus b. Okay, so we have 2 equations and 2 unknowns, and we can go ahead and solve that. Okay, so we could, in fact, what we could do is we could just subtract these 2 equations, maybe up this way. So take this one and subtract that one, and we'd end up getting 3 to the n minus 1 is equal to, notice, subtract that, you get 2a, and then that subtracts out. So that means a is simply equal to 3 to the n minus 1 over 2. Hey, that's pretty close to what we got, but we're not quite done yet. All right, but we're getting very close. All right, now b, what's b? In this relation, well, it's just you take what a is, say 1 minus what a is if you solve for it right here. So so then we'd end up getting, and I'll put the work right here, kind of keep what we're doing here. Okay, so we have okay, so we have a minus, yeah, so we have 1 minus a, so that would be 2. So that would be like putting a 2 in the numerator and subtracting off 3 to the n and adding 1. Okay. And so that would be like 3. Okay, so that's what b is equal to. Okay, but we may not even need what b is because we know the answer is embedded in a, but we'll do this anyway. Just see what we get. 3 minus 3 to the n all over 2. Let's just keep that as is. So b. Now, let's come back to this computation over here. All right. So we know that this matrix raised to the nth power can be substituted by a times the matrix plus a diagonal matrix with these b's in it. All right. So let's think about that. So if we take a times that matrix, so think about this, it's like ax plus b. So a times the matrix, a is that, is this thing right here. Okay, so we have, I guess down here, 3 to the n minus 1. So we have 3 to the n minus 1 over 2. And you multiply it into this matrix, we're going to have a 0. Okay, we're going to have a 0 there, and multiply it in. And then that's going to be -3 times that value. And then a 4 times that value. And then you take this, you add b to it. So basically it's just adding b to the diagonals. I'm just going to put, for now, let's just remember what b is, and I'm just going to put it in right here. So it's b, I'm just adding b to it. And I guess I could have done that with a too, but I put it in. Okay, so I added b to those entries. Now, so this right here represents this part of the part. But notice we're only taking the top row because we're multiplying on the left by this. So really in our computation, all that's really necessary is just the B and the A like that, which is great. Okay, so it's just B, and then we're multiplying that by A0 and A1. Well, let's remember what A0 was. In the original problem, and I'll point this out right now, A0 was actually equal to 0. And in the original recurrence relation, let's remember what that was. That was A sub n is equal to, or A plus 1, sorry, is equal to an plus 3 to the n. So that tells us what A1 is, because you're going to get 0, so that's 0 plus just 1. So this right here is going to be replaced by 0, 1. And notice in this matrix multiplication, it just picks out that guy. Okay. And so that should be the result. And that's exactly what we wanted. Okay. And that is the formula that we were trying to get. And we just showed it, but we did it by having some fun with matrix powers and showed, yes, indeed, we really do get the same thing that a partial sum of geometric series would ensure if you looked at it. And I'm not going over that technique right now, but that's another way of doing this. This method can be applied in other situations. Kind of fun. Even if you have a recurrence relation that's non-homogeneous, you can sometimes, through a series and polynomial manipulations, turn it into a homogeneous system where you can use a matrix and get a power and find your formula. Thanks for watching.